Okay, I hope you can hear me, and I hope you can also see my screen. And now,
Yes, we can.
okay. Good. And can you see my pointer?
Yes, also.
Okay, great. So thanks for the opportunity to present the content of our paper here. I first want to introduce you to the co-authors, which are Antje Kilias, Susanne Turk, Nicole Bahayer, and Patrick Ute. And now I would like to present you something about the CA2 region in epilepsy. So first of all, as an introduction to epilepsy, around 3% of the world's population suffer from at least one seizure in their life, and about 1% is diagnosed with epilepsy. So among all those epilepsies, there's a large percentage of epilepsies with a genetic background. And then there's a series of epilepsy that goes along with some brain damage like trauma or stroke, and some with also birth defects or developmental defects. And then there's a group of focal epilepsies with MRI detectable lesions. And among these, the mesial temporal lobe epilepsy, or MTLE, with hippocampal sclerosis is the most common one in adult patients, and it has a prevalence of 0.5 to 0.7 of 1,000 people. In humans, this disease starts more or less, not always, but very often with an initial event like a febrile seizure or some brain inflammation during early childhood. It is followed by a latent phase in which people don't really recognize any seizures or something. And then at the age of puberty or around puberty, recurrent seizures come up. And these become later on pharmacoresistant. So the standard anti-epileptic drugs do no longer work. And if you look at the hippocampi of these patients, either post-mortem or after surgery, which is one of the therapies that is applied, you see changes in the structure of the hippocampus, which are characterized as hippocampal sclerosis, which includes cellulose in CA3 and CA1, the preservation of CA2, and gliosis, which you can see in that Nissl staining. And in addition, there's a dispersion of the granule cell layer and the sprouting of the mossy fibers in patients, which you can also not see in the Nissl stain, but in synaptic stainings, for example. And the patients develop epileptic seizures. To shorten these 15 years, we look at a mouse model in which we inject kainate, so the glutamate receptor agonist kainate, into one hippocampus at an age of 8 to 12-week-old mice. We have a phase of epileptogenesis during which processes take place that I will introduce you later to. And after 14 days, we have a quite stable pattern of epileptic recurrent seizures, which are mostly pharmacoresistant. And similar to the patients, we also observe cell loss in CA3 and CA1 and a dispersion of the granule cell layer. And we were now looking at CA2 because CA2 is one of the regions that is claimed to be resistant towards the epilepsy-induced cell death. And we were looking at it in those mice. In that case, you see a control mouse in which the granule cells transgenically express Thy1, EGFP under the Thy1 promoter. So you see the granule cells and mossy fibers in green, and you see in red protein protein for staining for CA2. And after 7 days, we observe a preservation. 7 days after kainate, we really observe this preservation of the CA2 region. And if we now look at later stages, we observe the dispersion of the CA2 region at 14 days. So this happens between 7 and 14 days. And this is also the case at 21 days, where we see that dispersion, which no longer differs from the 14 days. And what you can also see here or here is that the mossy fibers seem to change in that model. And if you take a closer look at the mossy fibers, again, the CA2 granule cells in red and the mossy fibers in green with the EGFP expression, you see that the mossy fibers strongly invade the pyramidal cell layer of the CA2 regions, and that these little dots, the mossy fiber synapses, surround the CA2 pyramidal cell stomata. And in an additional staining with synaptoporine, which is a marker for the mossy fiber synapses, you see an overlap of these, showing that the synaptic apparatus, at least in parts, is intact in those sprouted mossy fibers in the CA2 region. Now, in the current paper, we were investigating the epileptic activity in this model. So we implanted electrodes into the dentate, gyrus, and CA2 of both hippocampi, and recorded at 2 days, 7 days, and 14 days, and in some mice also at 21 days after kainate. And what we saw was that already early after kainate injection, we see these little epileptiform spikes on the dentate gyrus trace, on CA2, and also in both hemispheres. And this gets more and more, so you see a development of the stable pattern of epileptic activity in the dentate of the ipsilateral injected hippocampus in CA2, but also in the contralateral side. And to make sure that the ipsilateral CA2 signal is a local signal that is really generated there and not just volume propagated from the granule cell, we implanted silicon probes into CA2 and recorded there. And when doing current source density analysis, we found this strong dipole between stratum lacunosum moleculare, where we saw a current sink at the beginning of the signal, and then we saw a later sink with quite a delay in SR, and we hypothesized that this early sink represents entorhinal input, while the later sink represents the input from the mossy fibers to CA2. And in general, this showed us that this is also a CA2 generated signal, which is not only volume propagated from the dentate. So then we automatically detected and classified the epileptic activity. And for that, we used a classifier that has been developed by Katharina Heining, who was formerly in Freiburg. And she wrote this algorithm that detects the epileptic spikes. And if these are closer together than inter-spike interval of 2.5 seconds, then they are grouped into a burst. And then these bursts are sorted with a self-organizing maps into nodes of bursts of different severity, and with hierarchical clustering. 3 different groups came up, which are mild epileptic activity, moderate epileptic activity, and severe epileptic activity. And such the nodes could be sorted back onto these groups. So each of the events now falls into one of those nodes, and then you can see whether it's mild, moderate, or severe classified. And we used this and did this detection separately for all channels, so IPSI and contralateral dentate and CA2, and detected this epileptic activity and classified it. And if you now look at that along the timeline from 48 or less hours after kainate injection to 21 days, we see a small increase of the time spent in any kind of epileptic activity, just detected, not yet classified, relative to the total recording time. And if we do this classification, we see that the mild events are strong at the early time point and then go down, while the more severe events go up and then stay at this higher level or go to some a bit lower constant phase. And this is the case for the dentate and also for CA2 in the ipsilateral hippocampus, which shows quite a similar behavior. And we were checking how likely is it to detect any kind of epileptic activity in ipsilateral CA2 if we detect severe epileptic activity in the ipsilateral dentate. And this was quite constant already from the beginning throughout the whole time that we investigated. And then we thought, how is it with the connection to the contralateral hippocampus? And for this, we used the mouse that we had received from Serena Dudek and Georgia Alexander. which is the amigo-2 eye-cree mouse that you've already heard about now. And we used a virus that induces TD tomato expression in the entire cell under the synapsin promoter, and then synaptophysin-bound EGFP, which is basically mostly, which is expressed in synaptic vesicles. So it's strong in synapses, but also everywhere else where vesicles are transported. And this is a frontal slice where you see the injection site on the in the ipsilateral CA2, and you see in control the projection to the contralateral hippocampus, which is preserved after kinase. And we thought this is even better to see in horizontal slices, so we took horizontal slices, and this is about the level, the anterior dorsoventral level of the injection site. And at that level, the cranial cell layer has quite a strange shape, which is this W-like shape here, but otherwise the hippocampus looks more or less normal, or as you know it. And here comparing control and kainate, in that case, you see the dispersion of the cranial cell layer here and the cells in CA3. You can also see here in the DAPI staining. And if you now only look at this TD tomato and synaptophysin-bound EGFP staining, you see that the projection to the contralateral hippocampus is weaker, but it is preserved under the epileptic conditions. And to quantify this, we took the intensity profiles from stratum oriens to stratum radiatum in CA2. And this is for the ipsilateral side, where under control conditions, we see the strong intensity in SO and a strong intensity again in SR or SL. And under kainate condition, this is a bit weaker. And in the contralateral hippocampus, if we now normalize it to the intensity in the ipsilateral hippocampus, as this might be different due to the dispersion and some cell loss in CA2, we see basically a comparable pattern between kainate and control. While in CA1, there is a difference, in particular on the ipsilateral side of the CA2 projections, which aligns nicely with the loss of CA1 pyramidal cells. So we were looking at the activity propagation to the contralateral hippocampus. And if we look at contralateral dentate, this looks quite similar as what we've seen for the ipsilateral hippocampus. But if we look at contralateral CA2, the number of, or the occupancy of the mild events is much higher and remains much higher throughout all the recording. And the number of severe events, or the occupancy of severe events, is much lower. Anyway, if we look at, again, the pattern, what happens if we have severe epileptic activity in the ipsilateral dentate, as I've shown you before for the ipsilateral CA2 and now for contralateral CA2, this is much lower. But if you look at severe epileptic activity in ipsilateral CA2 and what happens in contralateral CA2, we saw an increase over time. Although this pattern here was constant, this seems to increase. So we were wondering whether this somehow depends on inhibition or on changes in inhibition, in particular on the contralateral hippocampus. So what we did was using PCP4 stainings to determine where CA2 is located, and then using GAT67, so for the glutamic acid decarboxylase, which transfers glutamate to GABA, and is a marker for inhibitory neurons, and used in situ hybridizations for this GAT67, and then quantified cells specifically in CA2, in all layers of CA2. And along the time course that we've looked at, from 2 days to 21 days after kainate, and if we look at the ipsilateral CA2 region, we saw already 2 days after kainate a massive loss of this inhibitory interneurons, and this remained for all the time. And in some mice, we saw some recovery which still has to be determined where that exactly comes from at the late stage at 21 days. Whereas others had those low levels throughout the whole recording or whole observation time. And looking at the contralateral hippocampus for all those time points, we did not see a difference in the contralateral hippocampus throughout the whole time. So a lack of inhibition or a change in inhibition, at least in number of inhibitory neurons, cannot be the reason for this increase. So there seems to be probably some strengthening of the synapses, which we still have to determine. And similarly, there's also something going on which is special, which is an increase in the likelihood to detect epileptic activity in ipsilateral dentate if there's severe epileptic activity in ipsilateral CA2. And this is also something that we are currently investigating, what underlies this pattern. So we were not only looking at epileptic activity, but also wondering what happens to all of that network outside epileptic activity. And we selected theta oscillations, as this is also some prominent type of typical hippocampal activity during spatial exploration. And we selected these theta episodes and did filtering for theta oscillations between 5 and 12 Hertz. And we were checking how big is the fraction of theta episodes of the total recording time. And this was increasing from 48 hours to 21 days, although due to a very high variability among all those different epileptic animals, this was not significant. Still, the means were increasing. And then we were selecting, or then we were testing with autocorrelation and with power spectral density, whether we see power spectra peaks in the theta range. And at 48 hours after kainate, we had to sort out quite a lot of the mice or the recording sites as you see them presented here. So at 48 hours, this seems disturbed in many mice. And in those where it wasn't disturbed, we saw that nice theta peak and took these for the analysis. But then at 7, 14, and 21 days, we had strong theta peaks and also these strong secondary maxima between 80 and 200 milliseconds. It shows that it's theta oscillations in the autocorrelation. So, I forgot that. We also did power spectral density analysis of theta oscillations to make again sure that we see dipoles and that we have a local theta oscillation in CA2. And then we knew from an earlier paper that Antje did before, and that was also published in Hippocampus, that in these epileptic mice, which is similar to epileptic patients, the theta oscillations are slowed down, and we knew that for the dentate. And so we were wondering whether this is dentate specific or whether it's also in CA2, and whether it is affects one only the injected or both hemispheres. And here you see in gray the theta frequency distribution for controls. And you see the mean for the kainate of this previous paper. And in those colored dots, you see the areas, so dentate, CA1, CA2, IPSI, dentate contra, and CA2 contra. And you see that already from this early time point, 48 hours after kainate, until 21 days, this theta oscillation is reduced by more than 1 Hertz, and this is constantly, and it's all over the network. So it must rather be somewhere in the entire theta generation network where something goes wrong here. So what I showed you today and what we've presented in that paper is that the pattern of the hippocampus changes quite a bit with cell loss in CA1 and CA3, dispersion of the cranial cells and dispersion of CA2 with multifiber sprouting. And I've shown you that CA2 is an active part of the epileptic network, that it might contribute to the propagation of EA2, so epileptic activity, to brain areas beyond the sclerotic hippocampus, like, for example, the contralateral hippocampus, and that early SE or early status epilepticus induced cell death plays an important role for epileptic and theta activity in CA2, since we observe all these changes already very early on. And so they can't depend on mossifiber sprouting, but rather on this early cell line. And since we started today with human CA2, the question is what happens to human CA2 in epilepsy, and this is an RGS14 in situ hybridization in human tissue, and this is a case where there is a patient that had epilepsy, but it was later on classified according to the cellular pattern as sclerosis only, so no hippocampal sclerosis, and in that you see the location of the RGS14 positive cells in CA2. And depending on the grade of sclerosis, so low grade or high grade sclerosis, there is a partial cell loss of the CA2 pyramidal cells, but there's also a partial preservation of CA2 pyramidal cells, and this depends on the grade of sclerosis in the total hippocampus. And that we could also observe there, looking at synaptopurine stainings, although these are definitely not an ideal staining for mossifiber synapses, that the mossifibers also tend to invade and to get messy around CA2 here and to invade the CA2 pyramidal cell layer. So there's also mossifiber sprouting in CA2 in patients. Yeah, and so much for today. I want to thank everybody who contributed to this study and also the previous ones that I showed you, and also the neurosurgeons and neuropathology that provides us with the surgical tissue. And thank you for your attention and for staying so long.